Okay, I want to wrap this up with some nice applications to some antiderivatives that we use in this course, and maybe a comment on an immediate application in Calculus 2 of the mean value theorem. Oftentimes in homework, people just have you check that a function satisfies the mean value theorem or find the C that satisfies it, which is really just a way of like kind of getting you to remember what it says. But the real power is in what it proves for us, what we can use it to get. And so I just wanted to show you that because I think it's neat and I think it's worth appreciating here towards the end of the course, the power of using math to prove more math. Here's a big one that shows up in this course. Let's just suppose that the derivative of big F is little f. In other words, big F is the antiderivative of little f, and f is continuous. Then all antiderivatives of f have the same form, f of x plus c. So I don't know if this would bother you or not, but the idea that I can write every antiderivative, every function big F whose derivative is f, as one function plus a constant, that any such solution would differ by a constant. There's infinitely many, but they're all related by just adding or subtracting constants. And there are no others. This is the entire family. This is kind of a deep statement. And if you want to talk about, hey, what are the possible solutions to an equation, we need statements like this about the uniqueness, or did I really find all of them? And so, undoing a derivative, this is all of them. Find one way to undo it, and then add a constant. When you take its derivative, that constant goes away, like we've seen. And so that constant doesn't matter, but that's it. There aren't any other secret hiding one. Okay, so we're going to prove it right now. It doesn't take that long. Let's just suppose we have two different ones. This is a classic proof technique. Hey, we want to show there's only one. Well, suppose there's two. See what happens. What does it mean to be an antiderivative? It means if you take their derivative, you get back the original f. So they both have this property. And now we're going to play a similar game. We're going to say, let's look at their difference. So let's just call this g of x the difference of f1 and f2. Well, we want to use the mean value theorem. Let's take its derivative. If we take its derivative, then we get the derivative of the difference of the functions, which is just f prime, big F1 prime minus big F2 prime, and that should equal 0. Why? Because f1 prime and f2 prime both equal f of x. So now let's apply the mean value theorem, but in some interesting way. The derivative is always 0. Always. Which means that if I say f prime of c times b minus a, well, f prime of c is always going to be 0. So I don't even need to know what c is. I know what its derivative is. It's 0. That times b minus a should be equal to g of b minus g of a. So this is the mean value theorem where I already know what the derivative is. Well, if I solve for this, well, the left side's 0, so I get g of a equals g of b. But it didn't even matter which a and b I chose, right? If the difference is always 0, right, or rather if the derivative is always 0, then the average rate of change always has to be 0. The mean value theorem says it has to be. So, if every a and b are the same, what does that mean? What is our word for it being the same at every a and b? Well, it's a constant. G of x has to be a constant function. So let's just say g of x equals c for some constant. Well then, what does that mean? The difference of these two is equal to c. In other words, big F1 is equal to big F2 plus c. If there are two, the only relationship they can have is being different by a constant. That is all of the antiderivatives. Once you find one, you found them all, give or take a constant. This is a really clever application of the mean value theorem. And when you learn to appreciate math, you learn to appreciate this mix of like cleverness and beauty. And oftentimes there are complicated proofs that are more straightforward, and then there's sort of clever, beautiful proofs that really like get to the heart of what's happening. And this is kind of both. I don't expect that you'd be able to figure this out on your own right away, but it's worth taking a moment to see if you understand it and appreciate that they took the mean value theorem and kind of flipped it on its head. Said, hey, we know what that derivative is, so this has to be 0. Very neat. I'm just going to go ahead and tease you a little bit. Probably the next time you'll see the mean value theorem is in Calculus 2. And in Calculus 2, you learn that the antiderivative actually gives you the area under a curve. So finding things like areas and volumes becomes a question of, can you find an antiderivative? the proof that those two things are related, that area is related to derivatives, right? That the derivative of an area is this original function. What you need to do that, the mean value theorem. Another good reason to kind of finish up this quarter thinking about the mean value theorem. I hope that was interesting. I hope you gave yourself a little bit of time to appreciate it, but also I hope it's a little hard to think about, a little challenging, because in working through that initial confusion, that's how you build that muscle in your brain and you build comfort in actually reading those proofs that have been in your book throughout this whole journey, that are really the foundations of the math you're learning and the whys for what you're learning, not just the steps along the way or how to do the product or the quotient rule. All right? So I think math is beautiful, and I think the proofs and the structure is beautiful, more than any steps or solving problems, and hopefully someday you do too. That's it for this lesson.